and they present at the UTMIST annual showcase. The project showcase is an opportunity for this year's 6 project teams to present what they have worked on for the last 8 months in the field of practical and academic machine learning.
So this year, in addition to the projects, we also have a couple of awards. So as you can see, we have 4 award categories. There will be the Best Project Award, the Technical Wizard Award, the Potential Impact Award, and the Audience Choice Award. Winners of these awards will receive some special prizes from UTMIST. And winning some of these awards will also be something that the winner can showcase as part of their achievements for their projects. To assess these awards and the projects, we will also have a set of judging criteria. First, there's completion, which determines how complete the project is relative to the team's goals. There's technical implementation, which kind of covers how the project works and whether their idea comes to life with their demo. There's the potential impact category, which assesses how big of an impact of a business value or research value the project will create. And finally, overall, there's the pitch and presentation, which discusses how well the ideas were conveyed and whether the slides and presentation were coherent and convey the idea effectively.
Well, the next question is, who will be evaluating the projects based on this criteria? Fortunately, we have some awesome judges who have joined us and will be giving their valuable time to help evaluate these incredible projects. We have 4 awesome judges here, and I will now give the floor to them to introduce themselves. So Dalia, would you like to go ahead?
I was muted. There you go. Hello, everybody. Yeah, I'm so excited to be here. So my name is Dalia Shemshel, and as you can see, I'm a data scientist. I work at Bell. I work with network data, and I hold a master's in data science. I also have some more than 5 years of experience now teaching data science courses in Ryerson undergrad certificate. Done a bunch of researches. So I'm super excited to see the new fresh ideas today. Yeah, you can reach me out on LinkedIn, by the way, if anybody of you is interested, and excited to see what's coming today. Thanks.
Thank you, Dalia, for the introduction. Sheikh, would you like to go ahead?
Hi, everyone. My name is Sheikh Kader. I'm a machine learning architect at IBM. So I'm particularly working with IBM DB2 database product, where we are bringing machine learning capabilities to make the database more intelligent, at the same time helping the companies or the users of DB2 to deploy machine learning solutions or models in the database. I have done my master's from University of Waterloo. Currently, I'm also doing a part-time PhD at York on machine learning. And in addition to my engineering responsibility as IBM, I also manage a couple of research projects with some of our university partners in Canada. So I'm very excited to see all the great work that you guys have done.
Thank you, Sheikh, for your introduction. Dorje, would you like to go ahead?
Yeah, for sure. Thanks everyone for coming today, and really glad to be here along with Milan. We're both from AltaML. And yeah, it's I used to actually be VP of technical writing at UTMIST, so it's nice to see the club again. And yeah, it's myself, I'm a solutions consultant at the moment, and yeah, it's we use we deploy design machine learning solutions to solve a lot of industry problems, ranging from oil and gas to farming. And also financial services as well. And yeah, it's I'm excited to see all the projects today, and please reach out on LinkedIn if you have any questions about AltaML. And yeah, I'll pass it on to Milan.
Thank you so much, Dorje. Yeah, I think Dorje gave a really good summary of AltaML, but just to kind of reiterate some things. So my name is Milan, and I'm a senior machine learning developer at AltaML. I work very closely with Dorje on a variety of projects in different industries. A bit about my background: I do have a master's degree in electrical and computer engineering. I've been working more on the applied AI side now for just about 2-3 years now, and a variety of different industries, different types of projects. More recently, I'm taking on a leadership role with our initiative with the government of Alberta, leading the GovLab AI work. And really excited and happy to be here and contribute to the community. And I'm excited to see all the projects today. So yeah, best of luck, everyone. And thank you for this opportunity.
Thank you, Milan, for your introduction. And Dorje as well. We would like to thank all of the judges for giving their time to evaluating these projects and letting us as an audience learn from your feedback. So once again, we'd like to thank you for giving your time. At this point, we will allow the project teams to present their work. And after they're done, you as an audience and judges first, will have a chance to ask questions about the project at the end of each presentation. Without further ado, let's get started.
Thanks, Arsh. So introducing our first project team, Real-Time is a machine learning project for predicting home prices in the GTA. It's a significant improvement on their last year's project, Real Value, which focuses on more data this year than ever before. Thanks to the effective use of data from a variety of demographic and public sources and an iterative database update process, Real-Time is able to provide highly accurate home pricing decisions for brokerages and regular house owners alike. So now let's welcome our next project team.
Hello, judges. Thank you for giving us the opportunity to present our project. My name is Arsh.
I'm Super.
I'm Matthew.
I'm Leo.
And I'm Arhan.
We're super excited to present our project Real-Time, centered around home price prediction for brokerages and clients alike. Now, recently, housing prices in Toronto have been growing with extreme volatility. Prices jumped by nearly 30% in the last 2021 calendar year, and by over 25% just between July 2021 and January 2022. With such unpredictability in the market, brokerages and realtors have resorted to giving hunch price estimates. As a part-time realtor myself, I can testify to the fact that realtors are more concerned about what the market was and what the market will be rather than what the market currently is, which leads to a lack of data usage, and eventually their clients become worried about overpaying or underpaying for their dream home. Machine learning offers a promising alternative for housing price estimates, one that is data-driven, accurate, and constantly up to date. This is the premise of our project, Real-Time.
So Real-Time strongly builds upon our project from last year, Real Value, which followed a similar goal in predicting house prices. So our final result from Real Value in predicting house prices was a 15% mean absolute percentage error. We also handcrafted our dataset in Real Value, which only totaled to about 160 homes. One point to mention is that there was no specific time range when these houses were in the market. So we had no recently available GTA datasets. We also created what we called a 10-second form for clients, where they could provide their postal code, number of bedrooms, bathrooms, square footage, and images, and it would give back an estimate on the price of the home. So this year we have two major goals. The first is that we want to create a dataset workflow that's extensive, up to date, and ingest data from different sources. And one of the major points regarding this goal is that last year we only had 160 homes in Real Value. So we want to drastically improve this size. And we also want to ensure that these homes are up to date and follow the market for the house prices. The second goal is that we want to train a machine learning model capable of predicting houses in the range of 8% MAPE error. So here's a diagram of our overall database workflow. And I just want to mention that the database is one of the core aspects of this project, and it was something we were really lacking last year, and we want to build upon this year. Because without a solid database, it's really hard to achieve good results. So taking a look at the three smaller yellow boxes within the larger one, whenever we're given any sort of API, for example, the Realtor API, we'll first start off by fetching homes, fetching detailed information about these homes, as well as amenities and other data. And in every single step of this process, we're going to send all this information to our MongoDB database. And this whole process, illustrated by the larger yellow box, will be automated every 12 hours to ensure up-to-date information through a Google Cloud virtual machine, in which we'll set up the Docker files and run some GitHub actions. And now I'll pass it over to Arhan, who will go over the database that we created.
As the pair mentioned, last year, we only had
You're
Not-
muted, Arhan.
Arhan, you're muted. Just
Sorry about that. As the pair mentioned, last year we only had 160 homes. This year we have over 36,000 partial homes, which compared to last year is a 225-time increase. We are also using a NoSQL database to allow for partiality. Another important point to focus on is that last year we had only 6 attributes, whereas this year we have over 15 normal attributes and 80 amenity choices. And on top of this, our database also consists of 17,000 mostly complete homes. Now moving on to the aspects of training. If we decide to train without images, we find that our data set is significantly larger, as a lack of photo use leads to more overall usable homes. And another point to focus on is that there is an ease of use with non-CNN architectures. However, if we decide to train with images, we find that there is a significantly reduced dataset size due to lack of photos for choices. And so when we use non-neural net architectures, we often find that they need adjustments. On the other hand, however, we are allowed to use images as an input, which leads to a more accurate prediction.
So one of the most difficult aspects of our project was pre-processing, in which we processed information from a variety of sources into usable data for learning, for training. And we classified features and attributes, some of which Arhan touched upon, into 3 types: numerical features, which could be directly normalized; easy categorical discrete features, which could be directly one-hot encoded; and hard categorical features, which need further processing in order to be useful. And after processing all these features, we applied feature selection using tools such as box and whiskers plots and correlation plots in order to visualize categorical and numerical data. And using this, we were able to reduce the feature space by removing features which didn't significantly impact housing prices.
We have tested many models, and we found that these got a relatively small MAP error. Obviously, the model ensemble of regression trees has the least test MAP error, so we choose it as our best choice. This is what the ensemble of regression trees looks like. It consists of a bunch of decision trees fitted into the dataset, of which the output are averaged in order to produce the final result.
So an interesting question is how we could incorporate images into our machine learning architecture. And for neural networks, images are usually incorporated using convolutional neural networks, which is what we did last year. But for traditional machine learning models, such as the ones that Leo mentioned, an alternative is required, as Arhan touched upon. And in order to do this, we trained an autoencoder on images in our data set. And after training the autoencoder, we only took the encoder part of the autoencoder and fed an image into that. The output of that is a low-dimensional vector representation of the image, which could be concatenated with statistical data and fed into our traditional machine learning model. So we found that training with images using an autoencoder produced better results, as you can see in the table. With photos, the MAPE was 1.5% smaller. But unfortunately, photos were not present for all house entries in the data set. And we also had some other features which suffered from the same problem. And so the next step would be to find homes with all features present.
So these are the key takeaways and the result of our project. API is really hard to find. For the Realtor API, we are band limited and it requires CORS authentication. For the demographic APIs, some of them charges a lot. Some of them are free, but with limited request quota. We need to spend time on figuring out how to get as many resources as possible with a limited request quota.
As previously mentioned, last year there were only 160 handcrafted homes, whereas this year we have created a novel self-updating GTA home dataset of over 36,000 homes and 50 attributes.
Cumulatively, this has led to a 6% MAPE improvement. And because of that, we have now passed the sub 10% MAPE level. At this point, we can consider real-time to be a highly accurate real estate price predictor. For example, on a 1 million home, the error is now less than 100,000, which is now a very informative estimate for a lot of different clients and brokerages. However, we're not satisfied and we want to continue improving on that result. Altogether, we learned that even with machine learning and differently properly tuning machine learning models, lots of high quality data is still what truly matters. And gathering up-to-date data from different sources is as much about software engineering as properly incorporating it with machine learning models. We also realized and confirmed that different feature types, including images, can help with test accuracy, and different model structures can be used to incorporate them into traditional and non-traditional machine learning models. At this point, we'd like to mention a company called Skyline AI, where they're doing something similar to us in the commercial real estate spaces. They provide estimates, predictive price insights for commercial real estate properties. And they were able to successfully incorporate different data sources, whether it be city APIs, commercial real estate information databases, and other aspects to provide highly accurate price insights. They were recently acquired at approximately a 30 million valuation by another larger commercial real estate company. And we feel our next step could very well be at that point. It's a matter of now incorporating more data sources and having more efficient API integrations into our database so that we can have as many complete homes as possible. So that concludes the core of our presentation. We'd like to demonstrate our website now as a proof of concept. So let me just share my screen here. So give me 1 second. So this is something that you can try out as well. I just sent the link in the chat. So feel free to head over to our website. And once you click the try it out page, you can notice that this is something that is comfortable for most users to fill out, where you have the number of bathrooms, number of bedrooms, postal codes, and you can see that there are a lot more examples of easy attributes, but still these attributes can be now actually used to inform your home price. And so you can feel free to try this out on your own website. It's a very simple form. And what we do is in the backend, we incorporate it with the variety of different APIs, including the Realtor API, along with the Overpass API, to fill in some of the information that is missing from this form. And something that you can do is just click submit. And once it just properly loads, you can see that it provides a highly accurate predicted price home estimate. And this is actually the price for homes around this area. If you go to the realtor.ca website, you'll notice that for 3-bedroom homes with a similar profile, this is around the price, which demonstrates its relative accuracy. We would still like to get better, but altogether, we believe that we've shown a proof of concept that not only brokerages can use, but clients can use to have confidence in buying their own dream home. With that, we conclude our presentation. Thank you for listening, and we now open the floor to questions.
I think we can go with some questions, right, the judges? Okay. So maybe I can start, and then maybe other judges will ask. So can you please explain that you wanted to include emails in your model as feature? Can you go back at that, how you anticipated those emails would help with model's accuracy?
Sure. So the idea was that we don't have images for all homes because to incorporate images requires some time, and that limited our data set for images. But we were able to incorporate them using different neural network architectures as shown here, and also through traditional machine learning models by feeding images through a pre-trained encoder, autoencoder specifically. And so that's an example of how we incorporated them. And we noticed the following results with the photo database. You can see that with photos on the same data set as without photos, the networks actually performed around 1.5% MAPE better, which is a pretty drastic improvement when you consider the use of one feature. So images help. However, for all houses, we didn't have images. And so our full data set of 17,000 houses, we weren't able to grab the whole, 6,000 is simply less than that. And so our results were eventually better with the full data set instead.
What I'm not much clear, and maybe you can explain that if someone is trying to buy a house, they would prefer the houses which has images. So it's more like they like image data, image along with the house listing. But I'm trying to understand how you see that emails will help with better price prediction, right, model.
Well, the fact of the matter is, right, that you said it yourself, right, that you want to buy houses that have good images within them, right? Like they have to look good, you know, in terms of like actually how they look. And we realized that while that's not the only thing that matters, like photos can help, like photos specifically, say frontal home photos, they can help. And so that's why we incorporated them into our different architectures through the use of whether I was coupling it with a CNN or running the image through an autoencoder and combining the input.
So is the goal here that you wanted to analyze the image quality and see if the quality of the image is higher? That means hopefully that will also impact or influence the price. Is that the idea here?
We wanted to test the impact of photos on the overall MAPE, whether including photos actually helps with the MAPE error.
I see. I do have a few more questions, but I'll get other judges to ask their questions, then I can come back.
Okay.
You can go ahead. I have a question for you guys. Great work so far, and I really like the results there. I'm curious to know, based on your work that you did last year, I know you kind of continued there, and one thing you talk about is the increase in the amount of data. And I think from this table, you can clearly see that even when going without photos, going between the 6,000 to the 17,000, there's even a big jump in performance improvement. I'm wondering if you did a comparison between how much work did you do on the architecture side of like different algorithms and different models versus using just more data? Like, have you looked at which is having a bigger impact on your performance?
We did. We actually did. We noticed that having more data is actually more helpful because of the fact that I mean, like I would be hypothesizing why, but we did realize that having more homes that the model can draw upon is better than having less homes with slightly better features.
Right. So okay, so that makes sense. And then comparing that to like what architect, so like really the emphasis is on the data collection part versus even just like the features or the architecture of the model.
Yeah, we realized that the data was actually what was hamstringing us last year, and like the core part of our project is actually the self-updating workflow that was able to automatically craft a 36,000 home data set.
Right on. Nice. Yeah, that's all for me. Thank you.
Can I go next for a question, please? I'm not going to take too long because I know Shay has more questions. I just want to know. Okay, so what you did here is you have one algorithm. You improved it by adding photo data because it correlates with prices, and then you take that algorithm. So when I'm on the website and I put okay, this is my home, blah blah blah. It's not online learning, right? It's the algorithm that here you're showing the. It's like a fixed set of algorithm that the best one, the 10.2%, the tree model that's trained on this 17,000. Okay, great. I have a question more on the business side. So what, and I know you mentioned a company that's doing that prediction, but why can't I go to? So your question is these are the houses that are not listed, right? So if I want to sell my house, I want to know how much it costs today, I'm going to use your tool to predict how much it's going to sell for, right? Is that it? Okay, got it. That's just because I was like, why don't I go to the MLE site and just look at the price? But okay, got it.
It provides more confidence because, well, like with respect, right? You have homes around the area that you're looking at. That's a very important factor, 100%. But at the same time, they're not quite the same in terms of housing, and like you do want to consider like different factors that are part of like the overall machine learning model. And so that's something like, I guess the machine learning model does things more holistically, which leads to, I guess, incorporating more data and relying on more data.
Yeah, that's great. Thank you. I was more concerned on the business use of that, but I get it now.
Got it. Because just one thing
Thank
to
you.
add, right, is that you can you can choose to use it as a client, right? To like see what your home is worth, but also as a realtor, you can kind of use it to provide like estimate.
To provide advice.
Yep,
right.
exactly.
Perfect.
Yeah.
Thank you, Ars.
Sheikh, I'm so sorry I have to cut you off. Unfortunately, you're muted at the moment because we're a bit over the question and answer time. So we will unfortunately have to move to the next group, but there will be a chance to ask questions afterwards. And if you do have any personal questions, you can feel free to directly message each of the project directors. But sorry to move on. Yeah.
No problem at all. I'll just include in my comments after the winners.
Great. All right, thank you. So with that, we'll move on to the next group. Yeah, and I'll also share, before that, I'll share the one-pager. Each group has created a one-pager that describes as a summary of their project. So feel free to have this in your local storage, just to sort of as a memory of what the project is. So with that, we'll move on to the next group. So an electrocardiogram, also known as an ECG, measures the electrical activity of the heart. ECG classification can be used by doctors because it can help them diagnose certain diseases. However, this is difficult, and automating the process can help them to quickly identify which type of ECG pattern a patient has. This motivates us to use machine learning models for ECG heartbeat classification. Today, the ECG analysis team will be presenting their work in developing ML models for this task. Let's welcome them onto the virtual floor.
All right, thank you, Arsh. I'm going to share my screen. All right, so good afternoon, everyone. Today we're going to present the ECG analysis project. Electrocardiodiagram, or ECG for short, measures the electrical activity of the heart. It can be used to diagnose cardiovascular diseases, such as cardiac arrhythmias. Unfortunately, distinguishing heartbeats on ECGs can be time-consuming because the signals usually contain a lot of noise, which significantly increases the time required for analyzing the ECG and the chance of misinterpretations. And this motivates us to develop a machine learning model to classify ECG heartbeats automatically. We're interested in comparing two different architectures and seeking the model that performs the best for heart arrhythmia classifications. So before we started implementing the models, we found two prior works that are related to ECG classification, and both of them obtained very good results. The first article we found is a deep convolutional neural network model to classify heartbeats. And this article proposed a CNN model to detect and classify cardiac arrhythmia into 5 categories. And the figure on the right illustrates the CNN structure. It was trained on the open source MIT BIH arrhythmia database. And the testing results of the model after training for 20 epochs is 94.03% and 93.47% on noisy and denoised ECGs respectively. And this work inspires our first approach to the classification problem, as the CNN model is easy to implement while producing good accuracy. Although CNN is well known for its outstanding capability of spatial information processing, it can process temporal data well. And some researchers argue that combining CNN with a RNN model would further improve the model's accuracy and robustness. So for instance, in the second article we found, Georgia's proposed a hybrid neural network for ECG classification. And the spatial features are initially extracted via CNN and are passed into a LSTM layer for temporal dynamics memorization. And the model was trained for 100 epochs and achieved an accuracy of 97.87%.
Thank you, Jan, for the overview. Before we started developing the model, we needed to pre-process the dataset, which was the same dataset as mentioned in the first paper, the MIT BIH open source arrhythmia dataset. But the dataset consisted of a complete long signal, and in real time, when we are diagnosing ECG signals, we also get a real-time stream of signals rather than individual heartbeats. Therefore, we needed to find a way to divide those, although there were divide those into individual heartbeats. Although there were expert marked heartbeat labels on the original ECG dataset, we chose to simulate a real-time environment by using the Pan-Tompkins algorithm on wavelet transform smooth ECG signals to divide and use that algorithm to divide the long ECG signal into individual heartbeats. Finally, because there were different labels of heartbeats, different numbers of each label of the heartbeats, we needed to oversample some of the imbalanced minority classes in order to address the issue of class imbalance and improve the accuracy of the model. In the beginning, we used a wavelet transform, which is an extension of the Fourier transform to limit the vanishing movements of the ECG signal. We simplified the ECG signal and smoothed the ECG wave. This way, we had a denoise ECG signal to train the model on. Next, we use the Pan-Tompkins algorithm in order to detect QRS complexes, which is another name for heartbeats essentially, and locate the and use that information to center each heartbeat around a reference point, which is called an R peak, which are these peaks that you can see on the ECG signal. To do that, we first differentiated the signal, which gave us a diagram as you can see on the right of the image, and then calculated a moving average on the square of that. And that way we had very conspicuous peaks, smooth conspicuous peaks on that moving average, which identified each URS complex. We found those peaks using wherever the derivative changed. So wherever it became negative to positive, we marked that as a peak. And then around those peaks, we located each heartbeat on the original signal by taking a maximum. After doing this, we had a rough indication of where each heartbeat was, but heartbeats can only occur once between each refractive period or the beating of the heart, a general indication of the pulse. So any heartbeat which occurred between those window size, we removed the smaller one as a T wave, which is another artifact that might be produced by ECG recording device. And then we did a signal. Then we used an adaptive noise algorithm to ensure that all the peaks were true R peaks rather than just noise. And to do that, we used an adaptive noise algorithm which changed its quality based on the amount of signal and the amount of noise at any point in the ECG signal. These are the final results of the Pan-Tompkins algorithm on our ECG dataset, which was the MIT BH dataset. These final detections were made extracted from a Colab notebook, and as you can see, most of the ECG labels were detected. I think the final accuracy was about 96%, and the green ones here, the green dots here are the expert marked labels, and the red dots here are the detections made by our algorithm, and they're very close. So yeah, we found that we still went forward with the Pan-Tompkins algorithm results because we thought that it would be more real time and would more properly simulate a real time environment of detecting ECGs.
Thanks, Manas. As Manas mentioned earlier, the next problem we had to solve was that of class imbalance. Nearly 90% of the ECGs from the database are non-ectopic heartbeats. So to prevent our model from overfitting and having suboptimal performance on minority classes, we generated synthetic data. While the authors of the first paper used Gaussian profiles for this, we found that oversampling from minority classes was just as effective in terms of model performance. We note that this data augmentation was only done on the training data to ensure that our test set contained only real ECGs. Next slide. Next slide. Okay, yeah. So the first model we implemented was the CNN architecture proposed in the first paper. The goal is to have the model learn appropriate filters to detect different kinds of abnormalities in the heartbeat sequences. The architecture used included 3 1D convolutional layers with leaky ReLU activations, each of which is followed by a max pooling operation to reduce the dimensionality of the feature maps. Finally, we have a 3-layer dense network, which then produces the model's output scores for each of the 5 labels mentioned earlier.
Initially, we picked the same hyperparameters as in the paper, but after some fine-tuning, we replaced SGD with Atom using the parameters shown due to improved performance. Now I pass it on to Thomas.
Thank you, Henny, for the overview of the first model. Now, before moving on to the second model, it is important to note some intuitive improvements that could have been made to this model. Firstly, it does not exploit the fact that data being passed to it is sequential in nature. And secondly, while the convolution kernels are capable of extracting local features of the data, they are not capturing the overall changes of the ECG, something that we judged important when classifying heartbeats. For those reasons, the team has also explored the second model. Next slide, thank you. The second model tries to address both of the issues discussed for the first model, while still leveraging the inductive biases from the first. To do this, an LSTM layer was introduced so that the model had a better capability of dealing with sequential data. The main idea here is that the CNN layers would extract local features and learn to automatically denoise the data, while the LSTM layers would capture its sequential nature. The model is similar to the first in regards to architecture, with the key difference being the LSTM layer that comes right after the CNN layers. The model starts with 3 convolutional layers with leaky ReLU activations for each, and each of those is followed by a max pooling layer. Following comes the key point of our architecture, the LSTM layer, and finally 2 dense linear layers that lead to the output of the model. This model is significantly larger than the first, with 69,000 parameters in total, more than a 3 times increase when compared to the 20,000 parameters of the first model. Now on to Nabil for the results.
So our CNN and LSTM models were trained for about 20 epochs. We opted to use the Atom optimizer instead of the SGD used by Akari et al. Because it allowed for significant improvements in performance. Both models use the cross entropy loss function and a learning rate of 0.01. Our CNN model outperformed the model proposed by Akari et al. In terms of model accuracy on both original and denoised test sets. Furthermore, it seems that denoising the ECG waveforms has little effect on model accuracy for both implementations, which indicates robustness in the models and agrees with the conclusions made by Akari et al. It must be noted that this improvement in accuracy is partially, next slide, please. It must be noted that this improvement in accuracy is partially due to the fact that Akari et al. Evaluated their model on synthetically generated data. This allowed them to ensure that both test and training sets had a balanced class distribution. Our approach was to only use oversampling on the training set, which meant that our test set would have relatively more examples from the normal class than any other class. Because of this, reaching higher accuracy levels in the test set may have been an easier task for our models. Next slide. Furthermore, our simple CNN model is 2 times faster to train than the CNN LSTM model, implying that the CNN LSTM approach is more computationally expensive and power consuming. According to our experimental results, the CNN model might be more suitable for classifying ECGs. It achieves higher accuracy than other models, trains faster, is easy to implement, and is robust enough to noises in the database. On to the conclusion.
So to sum up, in this project, we implemented 2 deep learning models that can classify ECG heartbeats into 5 arrhythmia classes. The results have shown that 2 models performed equally well and are both robust to noises in the dataset. The CN model, although has fewer layers and easy structures, produces slightly higher accuracy overall. And our CN model also outperforms the model proposed by Ikaria in the first related work in terms of specificity and test accuracy. And we really appreciate you taking the time to watch our presentation. And now we're open to questions.
Yes, I can begin, if that's okay. So this is a very interesting problem that you guys have worked on. So my question is, my question has 2 parts. First, that you mentioned is an imbalanced data set, which means the positive plus and negative plus. What is the ratio between these 2 classes, majority and minority? And did you consider any other evaluation metrics besides accuracy?
I can answer the first part, if that's fine. Yeah, so as I mentioned, there's 5 different classes, and the majority class is the non-ectopic class, which is 90% in the entire data set. The rest of them are spread pretty much equally. So you have 2% is the S class, 7% is the V class, and the rest is shared among the other two.
Yes, but besides test accuracy, first we also gather the accuracy for each classes to make sure that our model achieves accuracy, not because it's only predict a lot of the N class. And also we used other metrics such as specificity, sensitivity, and PPV, which are also mentioned in the paper. We didn't include that in the presentation due to the time limit, but we include all the information we gather in the Medium article, and you can check it out if you're interested in it.
Good. Thanks.
Should I go? Okay. Thank you so much for the presentation. It was really interesting. My question is really more related to the business value. So I was just wondering, like, have you ever considered, and like, I was just wondering, like, what is like the future roadmap of this, like, of what you're doing, what you're doing today, and even like using from analyzing the ECG diagrams, are there any specific cardiovascular diseases that hospitals would like to, utilize this on, or is like, I'm just trying to figure out like what is the continuation of this?
Right. So the vascular diseases can be like classified into three categories. And one of them is the cardioarrhythmia, which is most related to ECG because it can be reflected very clearly on the ECG diagrams. And we're interested in this project, and we think it has business value because nowadays, application of machine learning in biomedical engineering is a very popular topic. And since I personally very interested in biology and taking a lot of bio and pharmacy courses, what I learned from the lectures is that we're thinking of using machine learning to achieve the personalized diagnosis possible. And so I'm thinking that applying machine learning in the ECG detection is, of course, a very important part of it. It can really speed up the process of diagnosis and also can make it more personalized in the future. And this, of course, could be a very important next step. Yes.
I would add that it can also correct expert misinterpretations in case an expert makes predictable misinterpretations or is susceptible to noise. Machine learning algorithms are generally less susceptible to noise and can help the expert, also aid the expert to make faster or probably even more accurate decisions.
One last thing to add, sorry, is I guess two parts on the business value and on the next steps. So for that, to kind of add on to what Manas was talking about is, normally it takes, you need ECGs can only read by like specialized radiologists, and it's a very lengthy process to read through the signals, whereas our trained models are relatively quick, are much quicker to arrive at a classification. So that points to the business value. In terms of our next steps, I mean, we trained on the MIT BH dataset, but there are many other data sets for heartbeat classification. And so what we need to do is, I mean, we got really good numbers for accuracy of the model, but another important metric to understand is how well does that model generalize to new data, right? So if our model was trained on a data set in like, in the Boston hospital, if we moved it to like a hospital in like, in some other country, I don't know, like, some other, like Australia or something like that, maybe the data is different, the ECG signals are different somehow, and it might not perform as well. So for our next step, we want to test our model on each of the models on different data sets to see how well they transfer, and how generalizable they are. So that would give us a better idea of how realistic it is to not only deploy it to somewhere here, maybe like in a Boston hospital, but throughout other areas around the globe.
Thank you.
Okay, so with that, we'll proceed to the next presentation. So first of all, just want to say thank you to the ECG group for presenting. I'll share their website and also their one-pager in case you'd like to have a memory of what they've done as part of their project this year. So yeah, I hope like everyone can see the ECG analysis project that I've shared. So yeah, just take a look at your own time. With that, we'll move on to the next group.
Great. Yeah, so our next team will be Wall Street Bots. And just for a quick introduction, the Wall Street Bots project was a challenge to building a stock trading platform using data analysis and machine learning methods. So the final product here aims to enable user authentication, perform trading, build portfolios, and use automatic portfolio balancing with one of their tested strategies on their own web platform. So with the goals of providing increased portfolio value, let's welcome our next project team.
Hi, everyone. We are the Wall Street Bots team, and we're going to present you the Wall Street Bot project. Are you a stock investor? Are you tired of watching your market 24/7 and worry about the next market crash? Do you want to lie on a couch and then your portfolio just go up to the moon without doing anything? Here we introduce Wall Street Bots, an automatic portfolio management platform that makes your investment worry-free. So what is Wall Street Bots? Wall Street Bots is a 6.5 months project made by 10 developers over 300 hours. Our web portion consists of user authentication, order placing, manual trading, and also portfolio management strategy selecting, and also a machine learning backend that use one of our tested portfolio management strategies to rebalance the portfolio for you. So due to the complexity of the project, we're only going to cover a portion of our interesting finding. So in this presentation, we're going to cover the background, the pipeline, and the data collection, 2 price prediction strategies we have implemented, and the 2 portfolio management strategies we have implemented. And at the very end, we'll have a demonstration of how our whole system working together.
So here I would like to introduce some background of our project. Historically, because of technical and financial constraints, algo trading has been mostly used by banks, hedge funds, and trading firms as opposed to retail investors. However, we believe that now is the perfect time to create a tool like Wall Street Bots to make algo trading as accessible to the retail investor as it is to these mega corporations. As more and more regular people enter the stock market in the post-COVID-19 era, retail investors now have more power to influence the market than ever before. In events like the GME short squeeze, these investors and traders have already proved that they can punish bad trading decisions made by institutional trading firms. We believe that with an individualized open source tool like Wall Street Bots, retail investors will have another tool in their pocket to strive in one of the most volatile markets in the past 100 years.
So here I'm going to introduce the pipeline of project. The pipeline is the essential part of project because it enables future upscaling and the implementation of strategy. So all of our strategies are implemented based on this pipeline. So for our pipeline, we have a regression part, which takes the indicators and also historical prices to make future price prediction and volatility prediction. Using these data, we can fit into a portfolio management algorithm using strategies such as Monte Carlo or equally weighted portfolio and balanced portfolio for the users. Another essential part of project is data collection. So for our project, we collect market data using Alpaca Market API that gives you stock indices and also fundamentals. We collect a variety of news sources from New York Times API and also scripting from Finviz. We get real-time news data from RSS feed from a variety of sources, and also Wall Street Bets daily discussions thread comment to get investor opinions. Here we're going to introduce the strategies.
So a study previously showed that there's a high correlation between the Dow Jones Index and Twitter post columnist sentiment. And that study achieved 87% trend prediction accuracy. So if the next day price is going to go up or down. But note that the testing data set is only over a very short span of 15 trading days during a time of low volatility. So the realistic accuracy should be much lower. Next slide, please. So our first strategy is predicting next day close price using natural language processing. For our approach, we first tried using sentiment scores of news articles to predict the returns of 50 tech stocks, but we failed mostly because by the efficient market hypothesis, we must have zero latency in order to make the trades before market adjusts to the news right away. So instead, we looked at the daily Reddit comments. Also, since the model used in the original study is closed source, we decided to use a different model. So we used the pre-trained FinBERT model, which is fine-tuned on using financial text on BERT to get the sentiment scores of the Reddit comments, along with their 768 dimension embeddings. So combined this with the past price and market indicators like VIX, which tracks volatility, and QQQ, which tracks NASDAQ, we tried to predict the next day closing price of GME. Since there aren't enough daily return data points for GME, because we only use the past 2 years to train, we augmented our data using other stocks with high correlation with GME, like Tesla, COS, AMC, and Apple. Next slide. So we took the input features and tried to predict the next day close of GME using all these models. The moving average was used as a benchmark strategy.
So our most successful model is the distilled version of the LSTM network created without the Finber embeddings with only 8 features each time step. The network structure is shown on the right. The test loss was able to converge as shown on the left, and we found the best model with 256 hidden dimensions using the data points of past 10 days to predict the next closing price. The reason that this worked and not the original LSTM network is because the full feature LSTM has n times 777 dimensions, and we only have a total of 600 data points after averaging each day's comments. Next slide, please. Overall, our best model achieved significantly greater validation trend accuracy than the benchmark, with a slight improvement in mean absolute percentage error. Note that compared to the Bolin study, our validation period is much longer and our benchmark accuracy is lower.
Something interesting of note here is that despite involving the same type of model, the LSTM model arguably yielded our worst results, while the LSTM distilled model yielded our best results. This is because the LSTM model used many more features, as we mentioned before, than the LSTM distilled model, even though we trained them for roughly the same amount of time. During our experiments, we found that Finber embeddings did not aid much in trend prediction. As such, even though the LSTM model involved a larger number of parameters, it would need longer to train, and the extra features it added did not contribute much to trend prediction, resulting in the performance discrepancy we observed. This kind of shows that even though the model is the same, a change in data set can result in a very high change in performance.
So our second price prediction strategy is using hidden Markov model for daily opening price prediction. So the figure here shows a standard hidden Markov model where the Z represents the hidden state at each time and Y represents the observation at each time. So in our context, the hidden states represent the underlying stock market condition and observations represent the stock prices. So one reason that we choose to use hidden Markov model is that instead of outputting a point prediction, it can output a normal distribution with a mean equals to the expected value of the stock price and variance proportional to its volatility. So our goal is to use the closing price on a minute basis to predict the next day's opening price. So in the training phase, we standardize the series of closing prices by subtracting the first closing price. And for evaluation, we use the mean squared error and trend prediction accuracy as our metrics. So if you go to the next slide, here's the result of training a hidden Markov model with 15 hidden states on the Microsoft stock prices from 2019 to 2021. So on the right, the blue and red curves pretty much overlap, which means the prediction using hidden Markov model is very close to the true values. And the numerical results for the mean squared error and trend prediction accuracy also show that the hidden Markov model outperforms the baseline model and the random guessing.
Moving on to portfolio balancing, given our predicted next day closing and opening price, and assuming we only take long positions, we built 2 portfolio allocation strategies. First is the equally weighted portfolio, where we invest equally in all the positive return stocks. The expected return of the entire portfolio would be the average of all the expected returns of the individual stocks, and the portfolio variance can be calculated using the formula on the slide and historical variances. The second strategy uses Monte Carlo simulation to get the max Sharpe ratio portfolio. The Sharpe ratio is a measure of risk-adjusted return, so the higher the better. And so we can approximate the max Sharpe portfolio by randomly assigning portfolio weights between 0 and 1, and then calculating the expected portfolio return and variance using the formula on the slide on the bottom, and then calculating the Sharpe ratio. We repeat this process with different weights to get the max Sharpe, the portfolio weightings for the max Sharpe portfolio. And the graph here is an example of a Monte Carlo portfolio set generated through this process. Expected return is on the y-axis and volatility is on the x-axis. And the red square corresponds to the max chart portfolio, and the blue is the minimum variance. So that's like the lowest risk. And once we get the optimal weightings, we can make the daily trades to get the optimal portfolio.
All right, here's a quick demonstration of our web app. So to log into our web app, you can simply create an account or log in through your Google account. After you log in, you'll be able to you'll be redirected to our dashboard page where you can insert your alpaca information to import your portfolio. And in the positions page, you can view the stocks in detail and also add stocks to watch list. And in the dashboard page, you can also change your trading strategies simply by selecting it in the drag down menu. This is a quick portfolio overview. Since the first day of our deployment, our strategy has been beating the SPY by around 1%. Like I think this in the first day it beats SPY by 2%, but on the second day it beats SPY by 1%. Even though this is like a low data set, it still shows that our strategy is working right now. So yeah, why use Robinhood when you can just use our awesome web app, Wall Street Bots? All right, thank you for listening to our presentation, and feel free to go to follow this step-by-step guide to also try it yourself, and please ask any questions.
Yeah, I just want to like add something else. So you actually need to use an Alpaca account, which is free. The reason we use this because it enables you to actually use real money in the future. So right now, Alpaca is a paper. It has two options. You can use this paper money account or use a real money account. So this is the reason why you must create an Alpaca account. But the account is free. Yeah, and yeah, thank you for watching the presentation.
I have one question. Can you explain why you needed to do this portfolio balancing?
Yes.
Why?
You can say it, yeah. Sorry.
Yeah. So why portfolio balancing is like every day we try to get the predicted prices of the next morning, like next open or next close, and then we need to make the appropriate trades, right? Like one way is to just like a benchmark could be just to equally like buy all the ones that you predict are going to give you returns, but it might be better to like allocate your portfolio in a way to maximize the Sharpe ratio, which is like a risk adjusted return. So it kind of like gives a return per like a unit a variance like risk.
Yeah, another thing I want to add is all the model we have, it has a positive expected value, but the problem is it's not guaranteed 100% correct trend prediction. So you actually need a portfolio management strategy to take account of the volatility of the stock and also the expected value to make the most appropriate distribution of your portfolio based on prediction.
Okay, thank you. That helps.
Thank you.
Sorry, Dalia, I think you're muted.
Oh, I think it's a microphone problem.
I can ask my question in the meantime, if that's okay. Yeah, yeah. It's more like a really simple question, but I was just wondering, like, I was wondering how different is how does this product meet customer needs in a way that is better than competitors or alternatives like as you mentioned, right? Like Robinhood, especially nowadays when all of these types of solutions are popping up on a day-to-day basis, right? Like I'm just more curious about how is this going to stay competitive? Just curious.
Yeah, so Robinhood is actually not a competitor. The reason for that is Robinhood is it's just a trading app that like allows you to trade, but this actually implements portfolio balancing strategy with a good expected value for future return. So I think that's the main difference, because normally you leave your money to a hedge fund where you don't have a choice for like what stock you buy or like what strategy you use. But with this, you have your it's more individualized. It's also open source. So I think that's the biggest difference between this project and what's on the market, like Robin Hood. Yeah.
Thank you.
Thank you.
Do I have time for a question?
Yeah, you can ask a question.
Yeah. Okay. So I just want to make sure I understand this process. So I want to invest money. I go to Alpaca, put money in, and then I decide which stocks I'm interested in, and then you're using the HMM model to predict the next day value of those, and you're giving me the risk assessment, right? Is that it?
Not the risk assessment, but it balanced the portfolio for you. So
you're balancing the portfolio.
I'm balancing the portfolio
based on the risk. That's sharp. Okay.
Yeah.
And then you're using this information in the HMM model to give me the predictions.
Yeah. So HMM model is one of the model. We also have other models to use. Yeah. Oh yeah. So if you go to our web app, okay, let's see it. Yeah. And if you go, actually not this, because like there's some problem right now. If you go sign in. Here I'll go with my account, right? This takes you to the portfolio page. Okay. So right now it's in the weekend, obviously I can trade, but like if this is a weekday, I can show you how like it's being balanced. So right now, it uses a moving average plus Sharpe ratio simulation, and I can change to one of the strategies I have implemented right now. Yeah. So I think that's
yeah.
We can
I caught on HMM because I love the Markov models, and I wanted to know, why is it performing better in your prediction? That I think I heard this in the presentation. So is it?
Okay. Yeah. Okay. So if you go to the slide, you're gonna see the HMM model is 66% accuracy, but like the deep neural network are like 61 at the best. But there's a big problem, the big difference between that. The HMM model is predicting the opening price, which is closer to the time of the last data point. But the deep neural network are predicting the closing price, which has more time for fluctuation and harder to predict. Yeah.
Okay. Thank you.
Okay, guys, just a heads up. I do think we have to move on since we're a little bit short on time at the moment. But if you guys do have more questions, please keep a note of them, and then you can ask at the end of the presentations. Sorry about that, guys.
Thank you, guys.
Thank you to the Wall Street Bots team for presenting their project. They also have a website and one pager that they'd like to share in case you would like to have a memory of their presentation following this meeting. So just give me 1 second to share their one pager and we'll get going to the next group. So hopefully everyone can see their one pager right now. So yeah, feel free to take a look on your own time if you'd like to learn more details about the project. With that, we'll move on to our next group. Second. So recognizing handwritten text is a long-studied problem in the field of machine learning, with one of the most well-known datasets being the MNIST for handwritten digits. While recognizing individual digits is a solved problem, scientists have been looking for ways of recognizing the full corpus of text at once, including paragraphs and lines, as it makes digitizing documents a lot easier. A solution to this problem, known as handwritten text recognition, will be presented today by our handwriting recognition team. Let's welcome them onto the virtual floor.
Hi, everyone. Welcome to our presentation for our UTMIST project, using deep learning for handwritten text recognition. My name is Justin. I am the director of the project, and I'm joined by my developers, Fernando, Kira, and Ishan. Armand is also a part of our group, but unfortunately he couldn't be here today. Next slide, please. So to start, we'll be providing an overview of our project, as well as the motivation behind it. We'll then discuss related work, followed by a breakdown of the two portions of the model, which is a segmentation heuristic algorithm, followed by a classification network. We'll then talk about the training and results of the project, and we'll end with a quick demo. Next slide, please.
So as Arsh mentioned, HDR is a long-studied problem in machine learning, and it remains one of the most challenging subproblems of OCR because of the high variance in handwriting styles from person to person. Our project aims to tackle this problem through a deep learning model which leverages recent advances in end-to-end transformer-based architecture. Next slide, please. So although HDR solutions do exist, they are far from perfect. More specifically, while converting individual characters is a solved problem, being able to convert entire pages of handwritten text remains a challenge. This is due to factors such as cursive writing, inconsistent separation of letters, and the variability in the rotation of characters. As a result, there continues to be ongoing development in this field. Being able to recognize full pages of text is key to digitizing documents and revolutionizing a variety of industries, such as healthcare, insurance, and banking. It also holds potential in assisting those with visual impairment. Next slide, please. Typically, HDR systems are divided into two modules. A detection module aims to localize blocks of text within the image, and the recognition module aims to understand and transcribe the detected text. A combined CNN and RNN architecture is used, where CNNs are used for image understanding and RNNs for text generation. Next slide, please. More recently, the use of hybrid transformer and CNN architecture has shown significant improvements in HDR models. To further improve this, recent studies have investigated the ability for transformers to replace these CNN backbones. This has resulted in the development of higher accuracy models, such as the TR-OCR, an end-to-end transformer-based architecture, which features both pre-trained image transformers and text transformers. This specific model served as the inspiration for our project. I'll now pass it back to Justin.
The algorithm used to perform the line segmentation portion of our project is based on the paper scale space techniques for word segmentation in handwritten documents. Prior to utilizing this algorithm, we initially used the IAM dataset to train a ResNet model to identify bounding boxes. However, we experimentally found that the model did not outperform alternative heuristics-based algorithms. The main idea of our algorithm is that it revolves around scale space, which involves developing a family of signals derived from text as details are progressively removed to create what the paper defines as logs. The segmentation involved deciphering the lines within a document, and in order to achieve this, vertical projection profiles are used, which sums over the pixel intensity values within a particular row of an image. The pixel intensity values can often contain some noise and are smoothened using a Gaussian filter. The lines are then identified by recognizing the local peaks in the projection profiles. Next slide, please.
So once we have the segmented version of the line of text, we need to find a way to create a final output from it. And this is where we use a transformer network. And however, we need to do some extra steps. And this is more or less the pipeline that we go through. So we have a line of text and we process this image into inputs that we can feed into the transformer, and the transformer is composed of encoder and an encoder and decoder. The encoder creates from the input an encoded form, and then the decoder takes this encoded form and creates a raw output that is like processed again into the final output. So in the next slide, we see how this is done in the paper. These images are taken directly from the TR-OCR paper. So we have a line of text, as you can see in the beginning, it's broken down into patches, and together with the position embeddings that like represent where in the original image these patches are taken from, they're fed into the encoder, that you have the encoder form, and then you go to the decoder. Both the encoder and the decoder are composed of stacks of feed-forward and multi-head attention layers, with the only difference being that the decoder also has mass multi-head attention mechanisms. Once our input is encoded and decoded, we have some raw output in the form that you can see at the bottom of the image. And then we finally process it to give a digitized version of the text that can be compared to our label. Now we'll go to a quick demo.
So this is a website. I'll press try it out, and this is the image we'll try to reconstruct and digitalize. I'll choose a file. and then I'll run it. Now the model will take time to process the input and get the output. Until then, I'm passing on to Justin to keep the presentation going.
So during training, only the classification portion of the model needed training, since the segmentation portion was a heuristics-based algorithm. The IAM dataset was separated using a 9:1 training validation split. And for the test dataset, a sample of 5 handwritten documents were used to evaluate the model as a whole, which also means that we could evaluate how the segmentation algorithm worked in conjunction with the classification network. To measure the accuracy of the model output, we use something called the character error, which is the Levy-Stein distance between the output and the ground truth label divided by the length of the ground truth label, and a recursive implementation of the Levy-Stein distance shown on the bottom right. During training, cross-entropy was used as a loss function, and Atom was used as the optimizer, with a learning rate of 1 to -5 and a weight decay of 1 to -4. The inverse square scheduler was used as the learning rate scheduler, with a warm-up learning rate of 1 to -8 and 500 warm-up updates. And the model was trained over 50 epochs and a batch size of 2. Next slide, please. In the end, our project was able to predict the text from the test documents fairly well. The outputs from the test documents had an average character error of 0.17. And for reference, the character error of an output Hyundai and a ground truth label Honda would have a character error of 0.6. After training the model, the average training cross-entropy loss was 0.118, and the final average validation loss was 0.386. However, so far the data used was either pre-segmented text lines or documents where the text lines were reasonably on level, i.e. parallel to the page and not slanted. And the model does not perform as well when the text lines are not on level due to the limitations of the segmentation algorithm. And we'll now show the results of our demo.
So these are the results of the demo. I'll pass it on to Justin to walk through some of the results and errors.
So as you can see, there's still some errors, such as some words seem to appear out of nowhere, like the number 891. This is likely because during the segmentation, some portions of the above or bottom text line were included in that current text line. So those like little fragments of other text lines were perceived as individual words. But overall, long, complicated sentences such as imagine a vast sheet of paper on which straight. So that text line is read very accurately. And now I'll pass it back to Ishan to finish off our presentation.
So as you can see, the accuracy is really good. And as Kyra said, we are looking forward it to be used in healthcare, insurance, and banking fields, and many more fields. And looking forward, we see this model being used in archiving historical handwritten documents and making analysis of handwritten documents such as doctor notes or student papers. And there are many other possibilities. So thank you for listening to our presentation. And now we are opening the floor for questions.
Do I go first? Okay. Can you explain how you have come up, how you have chosen the hyperparameters values, such as the learning rate, optimizer, number of epochs? So how did you come up with those values?
Yeah, so one important thing to note is that unfortunately the project has some constraints. A big one was actually financial constraints. And since we had to use online computing resources, we unfortunately could only train it one time. And these hyperparameters were the ones that were used in the original TR-OCR paper. So when we trained it, because they worked well and they outputted a good character error, we decided to move forward with these hyperparameters. But given more monetary resources and time, we would certainly try out a hyperparameter search. to find out the exact ones that work best.
Can I go next? Is there any other questions? Yeah, so my question is, great job. So what you did is you replicated that paper, right? That's the gist of it. Is there anything innovative that you added to that?
So the paper, it only recognizes pre-segmented lines. So our application, it combines the segmentation algorithm with the classification network.
Okay, thank you.
There's an audience question, which is asking, does the lighting of the text affect the output, say when comparing the text in a well-lit area versus a dim area?
Yeah, that's a great question. Overall, lighting wouldn't really affect the output from what we've seen. It would only affect it if there's like some glare. And in that case, it may cause the algorithm to recognize some spots of glare as it would either obscure some parts of the text, or it may add some noise, which may be perceived as additional words.
There's a question in the chat regarding how can U of T students join this project. So we'll, as a group, UTMIST has project applications open throughout the year, including for the upcoming 2022-2023 year. Yeah, we'll be talking about this at the end of the presentation. So stay tuned for more details there. Okay, so with that, we'll move on to the next group. I'll just share the I'll just share the website that the handwriting recognition group has created. So give me 1 second to provide that. And yeah, if you'd like to try out their model, you can eventually do so on their website and just learn more about their project. And they also have a one-pager that they'd like to share. So yeah, feel free to take a look at that one-pager if you'd like to remember details about it and also just learn more. So yep, with that, we'll move on to the next group.
Perfect. Great job, team. So next we will have the employee attrition team. The objective behind their project was to help companies understand how to retain their top talent, as their top talent provides the company its competitive advantage. So using machine learning and data analytics, the employee attrition team aims to identify areas of improvement across all departments of the company by determining factors which might be responsible for employee attrition in different teams. So now let's welcome them onto the stage to present their work.
Yep, thanks, Theo. So I think we'll start off by just getting our slides up. So if you want to just share your screen. Let me just double check if Asman's able to share her screen or not.
Sorry, I think there was a connection issue on my end. Sorry, did I miss anything? Or
no, we're just getting started.
Okay, sure. Thank you.
Okay, yeah, so we'll get started then. So hi, everyone. I hope everyone's having a good time just learning about the project so far. And next, we're going to be talking about our beginner-friendly project about predicting employee attrition factors. So I'll first of all just give a small overview of how the presentation is going to go. First, we're going to be talking a little bit about what exactly our project is, kind of the motivation behind the idea itself. Then we'll go into the data set and segue into the model architecture as well. I'll talk about some pre-processing steps that we did then. And then from there, we're going to talk about our classifiers, some clustering that we did, and then the results of the cluster analysis as well. And then we're going to just finish off with some next steps for the project.
So at the end of the day, good employees are the backbone to any successful company. They provide the company with productivity, innovation, and a competitive advantage in the industry. It's no understatement to say that employees are the single most important asset to any business. Despite recognizing the importance of employees, no automated process to predict employee attrition is known to be used by any company. As a result, organizations face large amounts of tangible and intangible costs due to high employee turnover rates. Using machine learning and data analytics, this project aims to identify areas of improvement across all departments of a company by determining which factors might be responsible for employee attrition in different teams. More specifically, we predicted combinations of factors responsible for large employee turnover rates. Such findings can be relayed to human resources teams to provide a better idea on how to increase their employee retention rate by making necessary improvements.
For this project, we have used the IBM HR dataset that contains information on 1,470 employees. The data has 35 features, where 9 of them are categorical and 26 of them are numerical. The data is mostly discrete, and the snippet here shows the statistical distribution of some of the features.
So next, I'll go through our model architecture for the entire project ourselves. So we're going to start off on the left-hand side where we have the raw data. And during our initial exploration, we noticed that our data set was actually imbalanced. There were more employees that did not quit when compared to those that did. And the research papers that we were referencing, they ran into a similar issue. So we chose to use smoke balancing, just like they did, as we wanted to closely reproduce the results. And then after that, we chose to encode our data using one-hot encoding. So our data had a lot of categorical variables, like Afnan just mentioned, and we knew that our classifiers would give better results with integer data instead. And then from there, we took our one-hot encoded data and we put it into our classifiers. So if you go to the next slide, we can just see kind of a little preview of all the classifiers that we used here. And again, we chose these because they were in our research papers that we were referencing. So if we go back to the architecture slide, we can see that after the classifiers, we only selected the predicted the employees that were predicted to quit, and we ran them through a k-means clustering algorithm to group them together and then find those similarities between the employees to find those factors in the end as well. And then we used TSNE to visualize our clusters as we had a very high dimensional data set, and we performed cluster analysis as well to determine those exact factors, which we're going to be talking about later. So diving right into our classifiers, we're going to start with our decision tree model here. So the reference research paper had a final accuracy about 81%, and we were able to improve upon that and increase it to about 89%. We did perform feature selection, which selected 9 features out of the total 35 that we had, and we did not end up using hyperparameter tuning because it didn't enhance the performance of the model.
Another model we explored is logistic regression. Our logistic regression model achieved a final accuracy of approximately 92%, which is a large improvement from the base logistic regression model's accuracy of 71% and the research paper's accuracy of 85%. To acquire such an accuracy, we tuned the model's hyperparameters as shown using random search cross-validation.
Our next model is an ensemble model, XGBoost. We have used a similar step where we have done feature selection and fine-tune the model. For the feature selection technique, we have used the XGBoost feature importance method, and we trained the model with 15-fold cross-validation, and we tuned the model with random search CV as well, with 5 of these parameters. So the final model had an accuracy of 92%, which is essentially 3% increase from the reference paper. Next up, we got the random forest model. We tried similar approach to train it. However, it being a tree-based model, the feature selection and the fine-tuning reduced the accuracy. And we just trained our base model on the 15-fold CV, and it gave us an accuracy of 30 and 93%, which is again like a 10% increase from the reference model.
The final model that we ran with was SVM, or support vector machine. The research paper had an accuracy of 85%, and our base model had a very low accuracy of 49% on our one-hot encoded data. But after we refined our model with feature selection and hyperparameter tuning, we found that the best model was with a linear kernel, and we had a final accuracy of roughly 92%. So the next phase of our project was looking at data clustering. So in clustering, we kind of used two main techniques. The first was k-means clustering, and we want to group these employees into three kind of distinct groups. So we use k equals 3 after generating an elbow plot and determining that to be our ideal number of clusters. And k-means is a centroid-based clustering method. And to visualize our data, we use TSNE, and TSNE is purely just to visualize data, and we have a multi-dimensional data of like 30 plus different columns. We want to plot it on a 2D axis. So we use this, and it's a form of unsupervised dimensionality reduction. And here you can see the various TSNE visualizations of our different classifier results.
In the last part of our project, we have done the cluster analysis, where we have found the combination of factors that Malia was touched upon while she was talking about the agenda. And yeah, and the factors essentially and the employees that may lead, that may quit. And yeah, for this, we have used the prediction found from the five classifiers and analyzed how the features vary across the 3 clusters. And then we identify the common features that were found important in all of our models. The way we have determined the importance is, as if you can see the salary rate here, you can see how the rate essentially varies across the 2 clusters. So similarly, we found the features that were that kind of had this kind of comparison across all of our 3 models. Oh, sorry, all of our 5 models, and we chose those common features. Here for the numerical features, the most important one were the age, distance, and the salary again. And here the box plot again you can see the comparison across the clusters. For the categorical features, we have visualized the features into their exploded levels. So for the overtime feature, for example, we had yes versus no, and then we kind of saw what's the membership count within this each clusters. And here you can see cluster 2 had the most overtime, and we're gonna go more detail right after this slide. Yeah, like I mentioned, I'm gonna go a bit more detail about the characteristics. Consist of mostly older male employees who are quite experienced in their role, and they all are also working for the company for the longest time and tend to do the most overtime. However, they are not getting promoted as much, and they also are the least paid cluster. So they're of course not satisfied with their job, which potentially may have led them to quit. Similar to the cluster 1, similar to cluster 0, the cluster 1 employees are also mostly male. However, they are younger in age, and they have been with the company for the shortest time. So they're working for the, and they're also part of the research and development department, and they hold the title of research scientist and the laboratory technician the most. And since they are one of the highest paid cluster, they also have the highest level of environmental satisfaction and job involvement. So we can potentially deduce that despite having high income and holding a high job position, these employees leave possibly due to having proper work-life balance. As we can see, they tend to do overtime a lot. For the last cluster, I'm going to pass it to Yinan.
Yeah, so for our 3rd cluster, we realized that they were a lot more balanced in terms of gender relative to the first 2. Additionally, a key defining feature of this cluster was just how often these people switched roles. Given that these employees often quit their job, it's actually surprising to us that they had such a high work-life balance and were actually mostly married inside our data sets. Finally, let's just talk a bit about the potential impact and future steps that we might take for our project. So firstly, the business value here is really the main focus of our project. And ideally, we could see business use our model in a way to analyze the employees' data and sort of predict or like analyze their turnover rates and use our models to hopefully reduce that number, right? Because naturally, it's a lot easier to and cheaper to keep an employee rather than to get a new one and provide him with all the interviews, the training, initiation, all of that, right? So yeah, businesses are constantly looking for ways to improve their workplace and really retain people, retain their culture. And that's how we add value here. So future steps to help us achieve this and include both further research first, and second, increasing the accessibility of our model. Firstly, future research could really be used to help us get more accurate predictions with different number of features. This could be done either through more sophisticated models such as neural networks and whatnot, or by going through more optimizations in our existing models. Another future step which we would really like to do is to increase the ease of use of our project and just make it a lot more accessible, a lot more easy for businesses to use, right? An example of how we can achieve this would just be, for example, by reducing the number of mandatory features so that you could have a different type of data set and whatnot, and you would still fit within our model, it would still work with our model, so that we could essentially just work with more businesses. And that's all for our presentation. Now we'll open the floor for you guys to ask us questions.
I can ask question, but I can give other judges to ask first.
I can go. I have one question. I'm kind of curious. When you presented the decision tree model, you sort of mentioned you picked 9 features there, and based on some selection criteria. Can you maybe expand on a little bit? What were the 9 features, and what was the selection criteria for that particular model that you went through?
So I can take that question. So for the decision tree model, we used a forward selection. So it kind of automatically determines the optimal number of features while maximizing the accuracy. And for specifically what those features are, I don't have them off the top of my head. But if you're open to it, I can send you like a list later on.
Cool. Awesome. Yeah, sounds good. No, I was just curious to know. Thank you for that.
For your k-means clustering, you have selected the value of 3. How did you come up with this number 3? Did you do any further validation that 3 is the right number?
Yeah, so we used an elbow plot for all of our classifiers after when we were beginning to cluster the predicted employees that were going to quit, and all of our classifiers, surprisingly, they had k equals to 3. We didn't do any further research into like validating that, but now that I'm thinking about it, we can use, I believe it's called a silhouette plot to kind of, again, validate that number.
If I heard correctly, did you mention that you tried elbow method?
Yep.
Okay, good.
Yes.
Thanks.
I actually have 3 questions. I hope we can, please stop me if we don't have time. But the first question is kind of in line to Milan's question, but I'm worried, what is your data source? Where did you get your data from?
This was essentially from Kaggle. So I think it was synthesized by IBM, I think a few years ago.
Okay, so an open source Kaggle. Okay. And my second question is this. So you did a prediction model, you did a clustering. The clustering, you did that on the predicted output, or you did this on the actual data?
No, we did it on the predicted output because we wanted it to be kind of like a workflow, so to speak. So in our end product, the user would just have to go and input one data set, and then it kind of takes the output of the classifier and then clusters upon that.
Okay, perfect. We don't have time for more, but thank you very much.
Yep, thank you.
Okay, we will address, unfortunately, the audience question later on. Feel free to message the project directors individually. With that, I will message their website though in the chat, because every project has a website, and it's quite interesting to see how they've showcased it. And yep, I'll also share their one-pager in the chat for your reference later on. So with that, we'll move to our final group, the smile detector team. So the smile detector team, their project is all about detecting and rating smiles. However, the novelty that they take to it is, instead of analyzing the images as a whole, they analyze the image through vectors and then analyze the vector specifically, leading to a high accuracy model that conducts inference at a fraction of the rate. So with that, we'll welcome the smile detection team onto the virtual floor.
Hello, can you guys hear me? Mic is working amazing. I think Noah's sharing the screen. So thank you for the warm welcome, everybody. And let's get started, so a bit behind. So I'll start first. My name is Daniel. I'm a second year CS student. Who's next?
My name is Noah. I'm the project director. I'm a first year CS student.
My name is Michelle. I'm a first year CS student.
And I'm Bradley, second year CS. It's great to meet y'all.
Yeah, so we have a bit of a small team, but we're still very proud of our work. So let's just jump right into it. Next slide, please. So a bit of our goals is that as a team, we're still pretty we're a lot younger than maybe some of the other team members, some of the other presentations, some other teams. So I would say for me personally, I never had any machine learning experience. We don't really know much about machine learning at all. So for me, this project was kind of an introduction to machine learning and machine learning models. Like, what is a model? What does it do? What is the math behind it? Like, what does a neural network look like, and how does that function? And also, I would say for me personally, and I know for some of the other teammates, our main interest in this project was to utilize data imaging and to utilize a video input or image input and see how we could use machine learning to kind of get information from that and how we can learn from that. Right. So, however, after researching models and researching the kind of product we want to develop and the goal of our project, we realized that some previous models were actually not as impressive or not as, I think, efficient as we wanted our model to be. So eventually our goals kind of shifted to more improving on previous developed models and trying to kind of add new features alongside these models that could detect smiles. So we'll talk more about this later. But essentially, we found out that our model can actually, we add a lot of new features onto the smile detection model, and hopefully that will be kind of the marketability, and the future use cases for that. So, and obviously we designed a web application for the project, so you'll be able to try it on the website yourself in a bit. So yeah, Noah's going to talk more about the actual model and the demo as well. He's next.
All right, so for the demo, our model is currently written in Python. So we're using Flask as a web framework, and we're basically hosting this all in Heroku. But for future cases, the model could just be used in a Python script and not actually hosted on the web, or even ran in an app. And basically right now our demo can detect if the user is smiling or not, and it analyzes the user engagement. So basically, well, I'll just launch the demo. Here. So this is our website. This lists all the strengths and improvements that we've done to the model. And there's also the GitHub and the Medium article. The write-up for our two-pager is actually in the GitHub, but I'll launch the demo. So basically our demo asks for a YouTube video link. This demo is basically demonstrating an application that could be engagement analysis. Say a company has like a commercial or an ad, they want to basically test how good their ad or how engaging it is. They can basically use this product on testers to basically calculate an engagement score, which is currently just the percentage of time the user is smiling over the course of the video. But later we can expand that to include other factors, especially because one of the main strengths of our model is that it can run with a lot less resources and a lot faster than previous ones. So that leaves a lot of room for measuring other factors and doing other analysis. So first just put in the YouTube video, launch it. I'm just gonna pause it. So basically it tracks my mouth. If I'm smiling, it shows up as green and that number goes up, which is basically the amount of time I spent smiling over the video. And when it's red, it's not smiling. And the video can actually play. I'm just keeping it paused right now. But that's basically our demo. And okay. Yep. Okay. So we basically trained the model on the Genki 4K data set, which is a data set of 4,000 images. It's actually displayed on the right. And we basically did an 80-20 split where we took 80% of the data to train the model and 20% to test it to validate it, which is where we got our 93% accuracy rating. And all these images were tagged with 0s and 1s for smiling versus not smiling. The first step of our process is to first get these images and run them through the DLib model, which basically puts the points, as you can see in the bottom right, it puts those points on the face. And basically, in order to scale all our data, we scaled it so these detected points were all the same size when converted because the images could be different sizes. And so by basically cropping to the box containing these points, we could deal with the face being in different positions. And then we also rotated it to make the nose bridge perfectly vertical. And that's points 51 to 54 on the nose. And we basically took that point data and used the points on the mouth to import into our model. And then that became a prediction of smile versus no smile. Previous models typically just take in the entire image and use that image to determine if it's smiling or not smiling. We first took another step to break down the image into just those few points in the mouth, which is only a few numbers, which is a lot smaller than an entire image file. So that allows us to process the image faster and use less resources than current models. And we use a C-support vector classification model, which basically maps all these points of smiling or not smiling that we trained on the rest of the data.
Now our model is fast and accurate. We had more than 93% accuracy rate on our data set, which is similar to most models that are geared towards the same task. Our main advantage, though, is in our speed. Our model performs detections in fractions of the time that other similar models take, with an average of 1.4147 milliseconds per image. This is fast enough to process live video data up to 707 frames per second, which is a lot of frames per second. What's interesting is that we get faster speeds on older computers too.
So our product has a lot of future use cases that we can see. For example, as we've discussed previously, how we have the demo as an engagement analysis, where let's say a marketing company wanted to see how engaging their product was, or look at an ad, we could give a focus group the ability to watch the ad with this face tracker on, and be able to see like the points at which they smiled, or like how much engagement there was. Some other things that we thought of were, for example, auto capture for pictures or videos. So making a photo app that would allow you to take a picture when someone is smiling. And so that would help, especially when taking pictures of like kids or babies, when it's really hard to get them to smile and to keep a consistent face for a long time. So being able to just do it as soon as it's there, as soon as it's ready and nice and easy is a really nice thing to have. Another thing that we saw it was in video editing and streaming purposes. On one hand, you could use it to select frames where people are smiling, or even use it for clipping in live streaming. In live streaming, when people would like have something exciting happen and they would smile, some software would be able to recognize that and provide a clip of the footage that had happened there, so that people could get the highlights of a stream. Another thing it could be used for is participation in like internet challenges for streamers, like so for example, a try not to laugh challenge, where instead of using some sort of arbitrary metric of deciding when one has laughed or one hasn't, you could give a local version of the model and allow someone to put the vectors on their let it use their webcam to see their face, and then from there have an empirical judge of what is considered smiling or not. And so that could help a lot with community engagement and all kinds of things like that. But yeah.
All right, so that's our presentation. Thanks for listening. I'll now leave the rest of the time for questions.
Love questions. We love answering questions. Ask us anything. Anything. Okay, I see Dalia has raised her hand.
Great presentation.
Thank you.
I like the idea a lot. I was actually thinking about something else that you can use this for. But my question is there anything else like this out there? I don't know of it. Do you know? Like that detects the smile real time and gives you that percentage of how much am I smiling?
Right.
Are you saying your innovation here is that you're quicker at detecting the smile?
Yeah, so essentially during like research and looking at the results, we did find a lot of other models that did smell detection. So I think a famous one was called MobileNet or something like that, where it would detect smiles and have a bunch of parameters to kind of, help them define what is considered a smile. So after researching that and looking at other models, a big portion of like updating our goal was finding out that these models not work in the way we thought they would, or work as effectively as we thought they would after reading through those research papers. So that helped us try to improve our model and try to make it faster, which is why we're now using facial mapping to take those localized vector points of your facial features like your mouth, your nose, cheekbones, eyebrows, etc., which is essentially why our model is so much faster, because instead of looking at the entire image and processing that image, we're now using the C-support vector machine to essentially just input, an array of vectors, and for each, distinct facial feature, facial point, and that way our model's faster. And it still upholds, it's still very accurate. So it has 93% accuracy. And the reason why we didn't include a graph was because for the MobileNet model, we couldn't figure out how to set that up locally. So while we did compare it, we found out that even on like an old computer, like Noah's old computer, it still actually performed faster than all of the MobileNet models, no matter what parameters we gave it. So it is still a lot faster than those other models that we did research and we did find, even when we ran our model on a slower machine, which we assume the other models will not run on.
Awesome. Thank you very much, Daniel. Good job.
Also, one other thing was the advantage to having, even if there are other models that can run at like 60 frames per second or like a normal amount of time. Also, ours is running hosted on Heroku, and even with the Zoom call running right now. And plus that leaves more room to do other calculations or analyze other factors at the same exact time you're running our model. When a traditional model would, if it can only run at like say 60 frames per second, once you go to do other calculations or add in more features, it would like slow it down and not be possible.
If you want to say that that your main focus is solving one problem, what is that one problem? Is it making your model run faster, or is it something else?
Well, I'd say it's making our model run faster and with less resources, so that if you want to apply it to like other advanced things such as engagement analysis or video editing with AI, you would be able to do things that you weren't able to do with slower models that might not even be able to run it live.
So on that, you mentioned that your model, you found it's faster than other model. So did you also compare the hardware specification of other people's models and yours, or how did you? Sorry, go ahead.
Yeah, so we don't have a direct like graphic comparison, because the models that we took, well, it's in the write-up on the GitHub. Like we found data from this other paper of current models and the speeds they were run at, and that was tested on, I forgot the model computer, but it's like a very high-end computer, which is a lot less powerful than mine. So we just said that it ran faster when tested on worse hardware versus better hardware. So we can't directly compare it unless we were to set up all those models on my computer and test those at the same time.
Okay. Any other questions?
I have one quick one. Just on your data that you used for training and testing, what was the balance of samples like? Was it 50-50 between like smile versus non-smile, or?
Yeah, it was roughly 50-50.
Yeah, I think it was like 53-47 specifically, if I remember correctly. But that the data set did not include only smiles. It also labeled pictures with like like other emotions, like, I don't know, being pensive, looking sad, things like that. So that data set, we did specifically like filter them to take a look at, the one is smiling, zero is not smiling, but that data set did also include other pictures that were, displaying other emotions and facial features.
And
So you
also
could extend it to do like multiple classification for different types of emotions.
Yeah, we could, but then we need to change the model throughout the entire thing. So future uses, we focus specifically on just smiling, but yeah, we could have changed the model to do other facial detections.
Yeah, and also the other thing was that those other models we compared it to also use the same data set that we did. So that's why we use this so we could like compare them a little better.
Awesome.
Okay. Sorry to interrupt you there, Milan, but we'll have to move on in the interest of time. So thank you to the Smile Detector group. I'm going to share their website where you can try out their work for yourself. And I'm also going to share their one-pager, and that's something that you can use for your future reference. So now with that, we'd like to thank all of the groups for giving their time to present their project. So thank you to all groups for demonstrating your work. Let's have a virtual round of applause to celebrate all of the unique achievements and the hard work behind all of these projects. Because I can personally testify to how every single one of these groups has put in a lot of hard work. And I hope that you were quite happy with their projects. And now at this point, we would like to thank everyone we would like to ask everyone specifically to fill out a Google form for the Audience Choice Award. And if you're a developer who's presented your project, it would be recommended that you do not vote. But if you are a regular audience member, please fill out the above form, and we will take a minute or two to collect some responses for the Audience Choice Award. So if you're having any form issues, let me know. A sign-in is required, but I think that should be relatively simple. Let me know if you have any questions. So we'll take a minute or two to do that. Yeah.
And in the meantime, I'm just going to remind the judges, if you haven't done so already, please make sure that you enter the separate meeting. I've sent the link in personal group chats. Yeah, you'll be doing your discussion there separately. Thank you.
Sorry, what is that link at the very beginning?
I don't see the link either. Yeah.
Check the Zoom chat on a personal one-on-one DM from me. If you'd like, I can resend it to both of you.
Let me check.
Yes, please.
No worries at all.
So we'll take one more minute for the audience poll. Feel free to choose what group that you thought had the best project. Okay. So. All right, so we'll wrap up the project form fill up in 10 seconds.
Thank you, Eka. Who wants to start?
Okay, so
like start with one of the awards, or I don't know how we want to structure it.
Yeah, perhaps start with the.
Who's just wondering who's speaking at the moment?
Sorry?
Who's speaking? I can't see the screen.
I think one of the judges is in the Zoom call and their mic is open.
It's actually very interesting because she's not actively in the Zoom call for me to remove her. Dahlia, if that's you, I'm not sure if you're accidentally on two Zoom calls simultaneously somehow. I'm going to request that you leave the current one.
Just remove me from the other one.
I'm trying, but I don't see you in the participants. I'm not sure how you're here.
I'm going in again. No worries.
Okay, thank you. And Sheikh, if you're having trouble accessing the link, would you like me to email it to you?
No, let me just drop and rejoin. I think I have the link.
Okay, awesome.
Sorry about that.
Zoom anomaly, for real.
While everyone else goes through the Zoom issues, For the audience here, we actually have something really special for you guys. So, we really appreciate how you've spent your time, dedicated listening to the presentations. And this goes for all of the developers as well of the different projects. So for you, and to test how well you've been listening to the projects, we have a Kahoot. It's a chance for you guys to gain some money, because there actually is a prize behind the Kahoot itself. So please join the Kahoot link, and let's have some fun with some questions regarding the projects itself. So I'll leave the floor open for approximately 2 to 3 minutes, and we'll go from there. By the way, there are actually prizes. I'm not saying that just to entice people. There are actually prizes. So yeah, please join. I'll leave the Kahoot open for a couple more, like a bit more time. So everyone can join, and we'll get started in around 15-20 seconds. All right, so we'll get started in 5, 4, 3, 2, 1. Okay. Ooh, okay. Well, yeah, lots of industries use handwritten text, including people in banking, finance, etc. So that was the right answer. Lots of industries. With that, we'll move to the first question. Noah is in first place, and yep, we'll go ahead. So this was actually a question on the harder side, but they ended up considering different models, but the core architecture that they ended up using was the Vision Transformer. So I hope that made sense. And with that, we have a new first, and let's continue on. So it was actually the BERT model that was used to convert news text and Reddit comments into sentence embeddings. LSTM was the model used for training it. But another difficult question. I only realized now and like a bit earlier just how difficult I might have made it. But yeah, hopefully it's been an interesting question, and we have a new first, Justin. With that, we'll continue. Yep, you guys heard that part right as part of the presentation. It was about recognizing a full corpus of text. So we have a really close battle here, and let's keep going. Wow, you guys more than I expected got it right. It was the Alpaca API, and that's what they use to automate that pipeline process for trading. All right, and with that, we'll move on to the next question. So it was the ensemble of regression trees that ended up being the best model for the real time. There's a really close battle here between Justin and Theo. They have to make sure that neither of them lose a question. So it's an interesting game for sure. So this was a really close one. Actually, images of faces is not fully incorrect, but at the same time, face vectors are their input type to the core small detection model. So with that, we'll go on to the next question. Yep, Sharp ratio. I expected this would be more difficult, but it was clear that you guys were paying attention during the presentation. We'll move on to the next question. All right. Yep, it was the Pan-Tompkins algorithm to detect R peaks specifically within the electrocardiograms. We have a new first, interesting. So let's see what happens next. Yep, it was 6 project teams that presented in this year's showcase. Super exciting projects that have been shown in this presentation, the showcase. All right, so next question. Yep, so it was the inference, the best one was actually less than 5 ms. They had approximately 1.4 ms per like overall to consider an image and to convert it into a classification. A really good rate. And it's actually like 0.5 was a commonly chosen approach as an option as well. But yeah, it was 1.4, so less than 5 at best applies. All right, so we have a new first. Theo's back in the lead. So with that, we'll move to the next question. Nice one. The core word being pinpoint here rather than predict, because the pinpointing was done by the clustering specifically. So with that, same first, and we'll move to the next next question. Yep. So this was a one that came up early in the showcase. It was 9%. 15% was the rate from last year, and it has been improved to 9% this year. So we again have a new first. Theo's in first, and with that we'll move on to the next presentation. Next question, so to speak. Yep, so LSTM was a close one. BERT was the one used to change embeddings into, sentences into embeddings. Yeah, comments into embeddings. And distilled LSTM was their best model. Okay, so that will move on to the next question. Close. 2015 is a pretty good choice. Unfortunately, it was 2017. So congrats to those who got it right. Oh, so we have our podium here. So third place is actually Theo. And second place is Kang. And in first place, we have, drum roll please, Justin. So congratulations, Justin, on winning the first prize with the runner-ups Matthew and Ving chilling. You'll actually get a special Amazon gift card from UTMIST, and congratulations on winning the competition. So with that, I hope you had a fun time. And give me 1 second to mute the music. Yeah, so I will forward the prize money to Justin, but thanks everyone for participating. And at this point, we'll wait on the judges to decide. So Kavya, if you could help with the music playlist, just to fill the time, that would be great. Or if anyone would like to discuss anything, feel free to put some questions in the chat. We'd be happy to answer them. Yeah.
Okay, cool. So Arsh, just a heads up, all of our judges are back in the room, so I think we can move on to the prize distribution and closing ceremonies.
Sounds good. Theo, would you like to go ahead?
Yeah, sure. So yeah, first of all, I'd like to thank everyone for just joining for this long project showcase. I hope you guys have all learned something from these amazing presentations so far. And also just congrats, shout out to Justin for winning the Kahoot competition. Good job on that. So at this point, the judges have decided on the award winners. So we'd like to give the stage to the judges so that they can present their awards.
Okay, I can go present the technical wizard. So first I got to say, really good job for all the teams. I mean, I was really impressed and blown away by all of the projects today, both from technical, from the business side, the demonstrations. I think everybody did a really impressive job, and yeah, big kudos to everyone. So this was a really hard decision, but ultimately what we decided for technical wizard, we've awarded the employee attrition team for technical wizard award. So congrats. Yeah.
Congratulations to the employee attrition team for winning the Technical Wizard Award. We'll move on to the next award.
A potential impact award, that one goes to Smile Detector, detecting and rating smiles. Good job.
Congratulations to the Smile Detector team for winning the Potential Impact Award. We'll go on to the next award. Who is presenting this award? Just want to make sure.
Well, this one should be us, right?
No, actually, it's so Sheikh, could you present the award, assuming you have the winner?
Yes. So for the Audience Choice Award, the winner is Wall Street Boards. Congratulations, team.
Congratulations to the Wall Street VOD team. And last but not least, the Best Project Award. So Delia, would you like to go ahead?
Is it me or is it Georgie who's?
Oh,
yeah.
sorry. Yeah, it was Dorje. Yeah, my apologies.
Yeah, go ahead.
Go ahead.
All good. Yeah, I just want to say again, like as Milan said, like thank you everyone for all your projects. It's extremely impressive. Like the judges, we had a tough time, so it was really great. Like thank you so much for your effort and time that you placed into it. Yeah, so Best Project Award. This one is going to the Real Estate Price Prediction project. Congratulations, really well done. Thank you.
Congratulations to the real-time team. And with that, we'll move forward in the presentation. First of all, congratulations to all of the award winners on demonstrating some remarkable achievements as part of the projects. Regardless of the awards won or not, I know that we can all agree that every project demonstrated today has an interesting machine learning application that has significant promise for the future. I can let the judges testify later on as part of their feedback how hard it was, in my opinion at least, deciding on some of the project winners because every single project I felt today had an extremely high level of quality. And so I would like to thank all of the projects and award winners for demonstrating some truly remarkable presentations today. So thank you to all projects. Furthermore, we would like to thank the judges for giving their time to listen to the presentation, evaluating their merits and points of improvement for them, and deciding on the award winners. In many ways, this showcase is not possible without you. So we would like to thank you for giving your time today to helping our project teams learn more about what they can do. We would also like to thank the audience for providing their time to listen to the presentations and participate in these showcase activities, whether it be the Kahoot or the audience vote. Your involvement in this project showcase helps to make it a very nice event every single year. So we would like to thank the audience for giving their time as well today. If you're interested in joining such a project or presenting your own machine learning project, UTMIST will open project director and developer applications in the coming months. We look forward to seeing your future participation in such a showcase. And these applications won't be opening up, say, in September. They'll be opening up in the next month or two. So just keep a lookout on the UTMIST website for more details on how you can get involved in these projects. So that's something to keep in mind for the future. With that, we will call a bittersweet ending to the project showcase to the audience specifically. At this point, we will limit the meeting groups to project directors and developers to receive feedback regarding their projects. Once again, thank you all for attending this presentation. And from all of us at UTMIST, we hope that you have a great weekend and an incredible summer. So take care. Yeah, and if you have any questions for any of the directors, feel free to message them personally. And that's somewhere that you can ask further questions about their project. I would recommend having their one-pagers so that you can remember what these projects did today. So thank you for everyone coming, and have a good day. Bye. We would like to ask all project directors and developers to stay for their feedback. And we had a planned method of doing this, and yeah, we'll kind of go per team and sort of just ask the judges to give feedback on where they thought the projects did well and what could be improved. And so we'll start from last to first. So in this case, judges, feel free to unmute, and you can, I believe the core directors for the employee attrition team are here. So feel free to provide some feedback to them if you would like.